Hi, hello, this is Srija from CSD C section department. I am here to say about graph of ultrametric type matrices. Ultrametric matrices are kinds of matrices or restrictions of non-singular tree matrices. The structure of AY1 allows us to associate to A some substochastic kernels P. We are able to describe the graph of P, in particular those vertices which lose mass. Ultrametric and gum matrices can be seen as the potential matrices of Markov chains on finite state spaces. In this chapter, we study the connections of these chains and emphasize the characterization of roots, which are those points where there is a loss of mass. This is equivalent to studying the incidence graph for the inverse matrix. The main notions and results of this chapter are based on for the ultrametric case and for the gum case. Introduction. Let I be a finite set. We denote n as less than I. Definition. A is an ultrametric matrix if it is symmetric, non-negative, and it verifies the ultrametric inequality. Aij greater than or equal to minimum Aik, Akj for any I, j, k belongs to I. Has this last inequality implies Aii a more restrictive class of matrices is given by A is a strictly ultrametric matrix if it is ultrametric and the strict inequality holds in 1.2 for every z into IGI. Definition 3. Definition 3. Let I be a set and T subset I into I be a non-oriented graph. That is, I comma j belongs to T. J comma I belongs to T. Then T is called a tree if it is connected and has no cycles of length greater than or equal to 3. That is, if for some S we have IQ comma IQ plus 1 belongs to T for Q is equals to 0 and up to S minus 1. I naught and up to is minus 1 are all different and is is equals to I0. Then s less than or equal to 2. Strictly ultrametric matrices were defined in as non-negative symmetric matrices A is equals to Aik whose entries satisfy the following inequalities: Aik greater than or equal to minimum Aij comma Ajk for all I comma j comma k. Aii greater than Aik for all I comma k comma I is not equals to k. The following theorem was proved in 3 and a linear algebra proof was given in theorem. Every strictly ultrametric matrix is non-singular and its inverse is a diagonally dominant M matrix. A construction also was given in to describe all such ultrametric matrices. Latter non-symmetric ultrametric matrices were independently defined in 4 and 6 and equality was allowed in 2 with additional constraints. We shall call such matrices ultrametric matrices. In the present note, we first deal with symmetric ultrametric matrices. We shall say that a symmetric ultrametric matrix is special if the following equality holds for all I. Aii is equals to max k is not equals to I aik. Such a matrix is in fact never non-singular but is always, as we shall show, the limit of a convergent sequence of matrices that are inverse of diagonally dominant M matrices. For the sake of brevity, we shall denote as Q the class of all inverse of weakly diagonally dominant non-singular M matrices, and as Q bar the closure of Q, that is the set of limits of convergent sequence of matrices in Q. Now let T be a tree on n vertices v1 and up to vn. Let e1 up to en minus 1 be its edges. We say that T is non-negatively edge weighted if a non-negative number wi is assigned to each other. Definition 4. A matrix A defined on I is equals to I is said to be a tree matrix if there exists a tree T I is equals to I and a non-negative non-decreasing function W 0 to 4 A are such that as W Z Z A in J T Q I J. Here is this graph of ultrametric type of matrices. On x-axis we have matrix size n, and on y-axis we have seconds. Matrix sizes are 2 cube, 2 power 5, 2 power 7, 2 power 9, 2 power 11, 2 power 13 and 2 power 15. And the seconds are from 10 to the power of minus 7, 10 to the power of minus 6, 10 to the power of minus 5, 10 to the power of minus 4, 10 to the power of minus 3, 10 to the power of minus 2, 10 to the power of minus 1, 10 to the power of 0, 10 to the power of 1 and 10 square. In this, the boxes indicates that first one ultrametric tree construction, second one ultrametric multiplication, third one ultrametric tree construction and multiplication, fourth is standard multiplication. In this article, we categorize generalized ultrametric matrices whose inverse are tree diagonal. This generalizes the results of McDonald, Nabin, Newman, Snyder, and Satsomeros for tridiagonal matrices. Ultrametric matrices. For any non-singular matrix A and A inverse, a diagonal dominant Stieltjes matrix, we consider P is equals to ID minus K inverse A inverse with K greater than 0, such that K greater than or equal to maximum A inverse I belongs to I. The matrices P are strictly substochastic, that is Pij greater than or equal to 0, summation j belongs to I less than or equal to 1 for all I belongs to I and R belongs to I, such that summation j belongs to I Prj less than 1. We use weighted directed graphs to introduce a class of non-negative matrices which under a simple condition are inverse matrices. We call our class the generalized ultrametric matrices since it contains the class of ultrametric matrices and some unsymmetric matrices. We show that a generalized ultrametric matrix is the inverse of a row and column diagonally dominant M matrix if and only if it contains non-zero row and no two of its rows are identical. This theorem generalizes the known result that a strictly ultrametric matrix is the inverse of a strictly diagonally dominant M matrix. We also present inequalities and conditions for equality among the entries of the inverse of a row diagonally dominant M matrix. Some of these inequalities and conditions for equality generalize results of Stieltjes on inverse of symmetric diagonally dominant M matrices. In 1887, in one of the earliest papers on M matrices, Stieltjes showed that the inverse of a non-singular symmetric diagonally dominant M matrix is a non-negative matrix whose diagonal entries are greater than or equal to the off-diagonal entries in the corresponding column, and he gave necessary and sufficient conditions for the equality to hold. In this, we generalize Stieltjes inequality to row diagonally dominant M matrices that may not be symmetric. We also generalize his conditions for equality to possibly unsymmetric row diagonally dominant M matrices in terms of certain axis relations of their graph. After we obtained some of the results, we learned that Nabhan and Varga have considered similar classes of matrices and that they have obtained some overlapping results. Definitions. We begin with some standard notation and definitions. Let x is equals to xij belongs to R. Let n is equals to 1 comma up to so on n. We let E denote the n cross 1 all ones vector so that xe is the vector of row sums of x. We also let P of x denote the spectral radius of x. We say x is positive x greater than 0 if xij greater than 0 for all I comma j belongs to n. Semi-positive x greater than 0 if xij greater than or equal to 0 for all I comma j belongs to n and x is not equals to 0, and non-negative x greater than or equal to 0 if xij greater than or equal to 0 for all I comma j belongs to n. We will write x to the power t to represent the transpose of x. We will write minimum of x is equals to minimum of xij I comma j belongs to n, and max of x is equals to max into xij I comma j belongs to n. We call x a Z matrix if x is equals to ai minus p for some a belongs to R with p non-negative. If in addition a greater than or less than rho into p, then we say x is an M matrix. We say an M matrix X is row diagonally dominant if xc greater than or equal to 0. We say x is strictly row diagonally dominant if xc greater than 0. Similarly, we say x is column diagonally dominant if x transpose is row diagonally dominant. These are some figures of ultrametric matrices. The minimal tree T transpose and the graph associated to P. Ultrametric matrices K into A ij is equals to K into A ij is equals to summation n greater than 0 Pn ij is equals to summation n greater than or equal to 0 pi into xn is equals to z. Summation is equals to summation n greater than or equal to 0 pi xtn is equals to z is equals to summation n greater than or equal to 0 pn into ij. Generalized ultrametric matrices. We begin this section by showing that a generalized ultrametric matrix can be represented by an isosceles graph and that it is permutation similar to a matrix in nested block form. Let C belongs to R and N be non-negative, then the following are equivalent. C is a generalized ultrametric matrix. Sigma C is an isosceles graph and Cii greater than or equal to max Cij, Cji for all I, j belongs to N. C is permutation similar to a matrix in nested block form. Begin by putting I belongs to alpha and j belongs to beta. For each k belongs to n, if I is a preferred vertex of I, j, k, then put k belongs to beta, otherwise put k belongs to alpha. We now show that alpha and beta are index sets for which 4.2 and 4.3 above are satisfied. Let I1 and I2 belongs to alpha by I and j1, j2 belongs to beta by j. Since sigma c is an isosceles graph, every triangle has a preferred vertex. We now sketch the ideas used to reduce the weights for the triangles. Note that this diagram only contains the edges which are used in the proof. The weights of delta ijji and delta ijj2, ijj1 and ijj2 are determined by the choices of j1, j2 belongs to beta, which imply that I is a preferred vertex in each case. The weights of delta iji1 and iji2 are determined by the choices of I1, I2 belongs to alpha, which imply that I is not a preferred vertex of either triangle, and the minimality of A plus B, which implies that J must be the only preferred vertex in each case. We can complete the diagram by observing that J is a preferred vertex of delta ji1, I2 and j1 is the only possible preferred vertex of delta I1, j1. Reading weights from the triangles using the condition that ckk greater than or equal to max ck1, cik for all k, l belongs to n, it is easy to verify that alpha and beta are as desired. Thus, A is an M matrix which is both row and column diagonally dominant as predicted by theorem. Moreover, the sum of the entries of A is 1 by 2 less than 1 is equals to minimum C as required. Note that row 1 of C has all its entries equal to C11 and Si is equals to 0 for all I is not equals to 1 as required by corollary applied to A transpose. R3 is equals to R4 is equals to 0 while R1 greater than 0 and R2 greater than 0. Vertices 3 and 4 do not access vertices 1 and 2 in G5 into A. We also note that C55 is equals to C45 is equals to C35 as required. Further, as required by corollary, since 4 does not have access to 3 in G5 into A, C43 minus C53. Since 3 has access to 4 in G5 into A, C34 greater than C54. Since 3 and 4 do not have access to 1 and 2 in G5 into A, it follows that C31 is equals to C41 is equals to C51 and C32 is equals to C42 is equals to C52. Theorem 1. Let A be an ultrametric matrix, then A is non-singular if and only if all its columns are different. If A is ultrametric and non-singular, then A inverse is a diagonal dominant stages matrix, that is summation j belongs to I, A inverse ij greater than or equal to 0 for every I belongs to I, and A transpose ij less than or equal to 0 if I is not equals to j. On the other hand, the non-singularity implies A inverse II greater than 0 for every I. Theorem 2. If A is non-singular tree matrix, then for all I is not equals to J, Pij greater than 0 implies I comma J belongs to T. Theorem 3. If A is an ultrametric positive non-singular matrix, then for all I is not equals to J, Pij greater than 0 if and only if the geodesic in T joining I and J does not contain a point in I other than I and J. That is GOED I comma J intersection I is equals to I comma J in the brackets. With this, I wind up this session. Thank you.